So we're going to talk now about how you can linearize your data if you're trying to plot some data that you expect from your model would follow an inverse function. So I've got an example data table here. The x values increase from 1 to 5. The y values decrease, and so that's a type of an inverse relationship happening there. I didn't put any units on x or y, so these could be any kind of numbers that you're trying to graph. So if you graph the data that is in that table, it looks like this. So x goes from 1 to 5, y decreases from 2 to 0.5, and you can see this is an inverse type graph. It's definitely not a linear relationship that's happening there, but it's some kind of an inverse function. So if you had a model for whatever this data described that you expected to be of this form, an inverse function, when we say that type of function, we mean y is some constant divided by x. So if that was the model that we had in mind to describe this data, one way to test that is to linearize your data. So on the next page we're going to take that same function and look at how to linearize it. So this is the same data table here. X has the same values and y has the same values, but I've added a new column that is the reciprocal of x. So I just took each x value and took 1 over x and made that column. So now if I think y is equal to c over x, might be the model for this, I can think of that as y is equal to c times the variable 1 over x. So now if I plot y on the y-axis, don't change that, but on the x-axis of my new graph, I'm going to plot 1 over x. You can think of it like we're letting z equal to 1 over x, and so y is equal to c times z, if you want to think of it that way. And so what I'm really plotting here is z on my new x-axis, and z is equal to 1 over x. Alright, so look at my new graph. On the x-axis, which is now my variable z is equal to 1 over x, I'm going to plot z. So when z is equal to 1, y is equal to 2.0. Alright, so I'll put that up here. Hopefully you can see my data dot. When z is equal to a half, y is equal to 1. So that's going to be about here on my graph. When z is 0.33, y is equal to 0.66. So I'm going to estimate 0.33 is about here. When z is 0.25, y is a half. That's about here. And when z is 0.2, y is 0.4. That's about here. So hopefully you can see on my new graph, it's definitely not an inverse function. I have linearized my graph by re-expressing the x data. And if I wanted to, with a ruler, or if I did this in Logger Pro, I could do a linear fit, and I could find the slope of that line. Well, hopefully you can see that by re-expressing this, see, we already know that we expect y is equal to c times z. That's a linear relationship, and the slope of this graph would just tell me my value of c. So since I picked the data so it falls exactly on a line, we could find that slope. In this case, the slope of this graph, I'll just pick 2 points. I'll pick delta y over delta z. The change in y between the beginning and ending points is 2.0 minus 0.4, which was my y value down here. The change in z is 1.0 minus 0.2, and so that comes out to be 1.6 over 0.8, which is 2. So in other words, going back to my original model, we've just found the value of c to be 2. So if I go back to my original model, you can see that really the function I've got here is the function y equals 2 over x. So one way to find to do a fit to an inverse function, as I've just showed you, is to linearize your x data by taking the reciprocal and then finding the slope of that new linear graph, and that slope is going to tell you the value of this constant in your inverse function. So now that you've seen an example of that, with this you can do the same thing with any time you have a data set where you expect an inverse relationship between two variables. You can re-express your data on the x-axis, call that z, which is 1 over x, and then you can find the constant in your inverse relation.